Let's talk about nucleophilic aromatic substitution. This is not your typical reaction of aromatic compounds. Aromatic compounds, as we've seen before with electrophilic aromatic substitution, can act as nucleophiles, attacking an electrophile and becoming substituted. However, in certain cases, nucleophiles can actually attack the aromatic ring. Let's look at an example. In this example, we have this aryl chloride undergoing substitution when treated with sodium methoxide. Notice we have an electron withdrawing group here. This is going to be critical to the mechanism. And on this side, we have a leaving group. Now the substitution pattern here is important. The leaving group needs to be para, or across from the electron withdrawing group. It can also have an electron withdrawing group adjacent to it, or in the ortho position. We need to look at mechanistically why this works. And you might be tempted to draw an Sn2 mechanism. Let's consider the Sn2 mechanism for a second. So our nucleophile would have to come in a backside attack to displace this chloride. Now, when we're looking at this, that means it would have to come completely through the aromatic ring, which sterically is not possible. So we'd have to attack like this. And geometrically, this just cannot occur. Never do Sn2 chemistry at an sp2 center. Okay, what about an Sn1 mechanism? For an Sn1 mechanism to occur, this halide would have to leave on its own. Now this aryl cation is pretty high energy. That doesn't mean it's impossible to form. We see it form from aryl diazonium salts, and I have a video on that mechanism if you're interested. However, halides are not good enough leaving groups to promote the formation of this aryl cation. So this is just a reaction that cannot occur. And before I throw away these mechanisms and ask you to erase them from your memory forever, I want to really point out Sn2 is for tetrahedral carbon, and it does not work with vinyl halides or aryl halides like we have here. Then how does this mechanism occur, and why do we need electron withdrawing groups? This reaction actually occurs by an addition-elimination mechanism. So our first stage of this is adding in methoxide. And we have this extended conjugated system going through the entire electron withdrawing group. So let me show some arrow pushing that explains why this can occur. First, we get attack at the carbon bearing the leaving group. These electrons are going to move over, and we can continue pushing all the way through our nitro group. We'll get an intermediate that looks like this. My nitrogen here had 4 bonds, and so I had to add on that positive charge and just added it back on in this structure as well. Okay, so this is the addition step. Our methoxide came in and utilizing this entire conjugated system was able to add. Now, if we push electrons back up, restoring aromaticity, we can kick out a leaving group. And this gives our substituted product. Now, I showed this mechanism by pushing electrons through the entire conjugated system, but if that's hard for you to see, I recommend drawing your mechanism 2 arrows at a time. And let's just do that to break it down even a little bit more and make sure we have our arrow pushing correct. So taking it 2 arrows at a time, first our nucleophile will attack here, and then we'll have to move these electrons onto this carbon atom. This arrow pushing gives us this compound. Now we can push electrons in here, making a double bond, and take the electrons from this double bond and push them onto the carbon. That gives this resonance form. And finally, still pushing 2 arrows at a time, we can make this a double bond and put the negative charge on oxygen and show how our nitro group is stabilizing this charge, just pushing 2 electrons at a time. That'll give us this resonance form. I want to highlight this resonance form here. Notice that we get buildup of negative charge on this carbon as well. And so this explains why an electron withdrawing group at the ortho position to the leaving group is also effective in promoting this reaction. We can stabilize an anion here. And notice we can stabilize an anion here with our nitro group, and we showed all that resonance. So that explains the positioning of 1 or 2 electron withdrawing groups on the ring. Let's look at an example with an ortho electron withdrawing group to illustrate the scope of this reaction a little more. Here, we're reacting this aryl fluoride with an ortho electron withdrawing group with sodium cyanide and getting replacement of the fluoride for cyanide. But you may be wondering why fluoride can undergo this reaction. Fluorine is a terrible leaving group in Sn2 reactions, so how is this possible? Well, in the mechanism, this step removes aromaticity from the compound, so this makes this into something that is not aromatic temporarily. This is hard. This is the difficult step. Therefore, that is the rate determining step. Now, elimination of the leaving group is fast. It restores aromaticity in the compound and is really favorable. So fluorine's only role in the rate determining step is being a very electronegative element that creates a great dipole here and makes this carbon even more electrophilic. Therefore, fluorine promotes this reaction very well because of its electronegativity. And because its poor leaving group ability is not part of the rate determining step, this reaction actually works great. Let's do a quick practice problem to see if you've got this down. Take a look at these 3 substrates. Pause the video if you need to and see if you can work out which of these is most likely to undergo nucleophilic aromatic substitution. Okay, so we're looking for the substrate with an electron withdrawing group. The first one is no good. This nitrogen has a lone pair that actually can donate electron density to the ring by resonance. This is not an electron withdrawing group. Now here, our chlorine is going to make this position more electrophilic due to its higher electronegativity. But the bromide, this is an inductive electron withdrawing group. So we do have an electron withdrawing group here. However, remember, bromine also has lone pairs. And this can donate electron density by resonance to the ring. So this isn't the most awesome electron withdrawing group since it just has the inductive electron withdrawing effect. Our winner is going to be the nitrile here with the cyano group on it. If we draw out this structure even more, we'll see we have this extra conjugation. So when a nucleophile attacks, we can actually push electrons through this entire conjugated system. Now, if you're having trouble figuring out which groups are electron withdrawing and which groups are electron donating and why, I highly recommend my video, Trick for Determining EWG versus EDG. I hope that you learned something and that you have a great day today.